Last time we were taking a look at section 4.4. We were looking at the Fundamental Theorem of Calculus. Let me remind you what that theorem said. That theorem talks about taking what's called a definite integral. So we do the integrals just like we did in section 1, antiderivatives. And then we have these limits of integration, these upper limit and these lower limit. And we're plugging in the upper limit into the antiderivative form and subtracting the lower limit plugged into the antiderivative form. And when we do that, we are going to then not need to do the plus c's. That's what we discovered, because they just subtract themselves out. So we get to avoid that step. And we had gotten to example number 5, which looks like this. So this one tells us to find the given area, and it gives us a description. It doesn't actually say the script S with the numbers and all of that. So we have to be a little bit more cautious of what we're actually looking at. So take your calculator. I know you probably know what this graph looks like, but in general, what we would do is we would take your calculator and take a look at the graph. And I think we have another one after this that we'll do this with as well. It's a little different actually, but we're going to take a look at this graph, and our graph is going to go it's going to be bounded with the curves y equal x squared and x equal to 2. So what does the graph of y equal x squared look like? It's a parabola, and where's its vertex? At the origin at 0, 0, yeah. So it looks like this, right? This is our graph. It says that we've got the line x equal to 2. Where is the line x equal to going to live? Good. It's a vertical line at the x value of 2. So something like this, right? So this is x equal to 2. This one's y equal to x squared. And the last one it gives us is the x-axis. So I'm going to redraw the x-axis in a different color just to be very clear for us. So it says it's supposed to be bounded by those 3 curves. So what I'm looking for is I'm looking for the area that's trapped between all 3 of them. Do you see it? Yeah. It's not a triangle, but it sort of has that same sort of a triangular-ish shape, right? So we're looking at this piece right here. So we kind of have this extra step on the front end of this one to actually set up what we're looking for in terms of the calculus components, correct? Got to start with the geometry, get the pieces all in there, and make sure that we have the right area of the curve. And now our antiderivative is, of course, of the curve x squared, and it is with respect to x dx. But we need the limits of integration, upper and lower, to be put onto there. 0 to 2, because we're looking at the x values, right? So the x value right here is 0, and the x value right here is 2. Does that make sense? Okay, cool. So now we're going to do the antiderivative from the front end of this all the way through. So what's the antiderivative of x squared? Okay, so it's 1/3 x cubed, or x cubed over 3 if you prefer. We draw the vertical line. If you remember from last time, we put the upper limit 2 at the top, the lower limit 0 at the bottom. And we're actually going to plug these numbers in. So we're going to do 1/3 2 cubed minus, and I know this one isn't very interesting, but in general we would want to do it. So it's 1/3 0 cubed. All right, so you have to write this down. You can plug it in your calculator, and what will you get? In non-repeating decimal form. Don't give me repeating decimals. What do you have? 8 over 3 is right, yeah. Did everybody get 8 over 3?
Yep.
All right, any questions on that one?
Is that it?
That's it. Yeah, so they aren't always going to be just nice, neat, pretty x squared, of course. There are going to be other things. But yeah, that is the process we would go through. All right, there's one more piece of information in this section that we're going to take a look at, and it's not a difficult thing. And there's a visual that I want to describe to you first. That I want to describe to you before we do our example. All right, so here we have, if f is integrable on AB, so that means we can integrate, then the average value of f on AB is 1 over b minus a integral from a to b of f of x dx. So let's take something near and dear to your hearts at this moment, your grades. How do you average your grades in a class? Yeah, at least in my class, right, where we're not doing percentages of everything, it's just all points, right? We add all the points together, and then we divide by the number of points, and then we would do a percentage form, right? Multiply it by 100 to get our percentage. But we take it all and we divide by the number of points. That's what's going on this formula. That 1 over b minus a is dividing by the width of your interval, right? So imagine what we've actually done here is we've said that our a is here and our b is here, and then b minus a is just the width of the interval. So that's what's going on here. We're averaging it by dividing by the width. Now, if you want to think about it in terms of the area picture that we've had, and I can just go back to this other picture that we had to kind of give you an idea, what we're kind of doing is we're taking this area and we're going to sort of cut off part of it and try and piece it in somewhere else to make a rectangle. That's what we're really doing. So there is going to be some location, and this might not be exactly it, but we're going to approximate and say that it's right here. That's a little bit high. Let me move it like this. That if I were to take the part that's above the black vertical or horizontal line, that red part, and I were to move it to the part below, I would have a rectangle that's the same area. Right? Imagine Play-Doh, right? Or dough, or silly putty, you know, something that's squishable. And you're just taking a portion of it and you're squishing it into this other shape, but it's the same amount of area as the first shape. That's what we're doing with average value. And I'll show you it in terms of a picture too, so that you can actually make sure when you're doing it that it makes sense. So we're going to actually do the formula first, and then we're going to look at a visual representation to see how it makes sense that works, okay? All right, so our formula says that we're supposed to be able to do 1 over b minus a. So what is b and what is a in this particular? 9 and 4. So this is 1 over 9 minus 4. We know that that's going to be 1 over 5, but I'm just writing it all out. Okay. Our integral goes from the 4 to the 9. And our formula, or our function, is the square root of x, but I'm going to write it as x to the 1/2 because it's easier for us to work with as we're integrating here in a minute. So far, so good? All right. What is the, well, this is 1/5 in front. What is the antiderivative, of x to the 1/2? Somebody said 2/3 x to the 3/2. All right, so if we add 1 to the 1/2, we get 3/2. If you divide by 3/2, it's the same as multiplying by 2/3. We are taking this antiderivatives, or we're evaluating this at 9 and 4. Let's say it that way. All right, so in front now I have 2 over 15. And in terms of plugging this back in, it really is helpful, truly, to put this back into the radical form, because this would be the square root of x cubed. And because of the numbers 9 and 4 that were given, it's actually really nice to think about the square root first and then the cubing second. So in other words, let me put the 9 and the 4 here. We're going to have 2 15ths, and then we're going to have the square root of 9 cubed minus 2 15ths, the square root of 4 cubed.
Wait, why is the cube on the outside?
It doesn't matter. The order of operations goes the same way because they're both exponents. The radical is an exponent and the cubing is an exponent. In some cases, it's more convenient to cube first. In this case, it's actually easier to square root first because the numbers will stay smaller. All right, so what's the square root of 9? 3, and then 3 cubed would be 27. So this is 2 over 15 times 27 minus. And then I have the square root of 4, which is 2, and 2 cubed, which is 8. And in fact, if you want to avoid the multiplying by the 2 over 15 and you actually want to do 27 minus 8 first, you could do that too, right? You can understand that this is actually the same as 2 over 15 and then 27 minus 8. Your calculator will handle all of it just fine, no problem, but any of those ways will work. Let me move it up here. I'm running out of space. What is 27 minus 8? 19, and then 19 times 2 would be 38. So this is actually 38 over 15. So that's the solution. What I'd like for you to do is to grab your calculator, okay? And I'd like for you to graph this equation, square root of x. Your interval needs to go from 4 to 9, but I want to make sure that your y-axis actually goes down to y equals 0. Otherwise, it's going to look funny, okay? So let me put mine in my calculator as well.
Where'd you say that was?
What's that?
The y?
I'd like the y-axis to be able to be seen. So let's just say our y goes from 0 to, well, let's see, we're going to have the square root at some point here of, 0 to 5 is probably sufficient. Right, too much paper in that screen. All right, so we have the square root of x. Our window needs to go from 4 to 9. And y-axis from 0 to 5 is probably sufficient. And let me just graph and let's just check it out. Yeah, that works great. Okay, so it almost looks linear in this screen, doesn't it? It almost looks like a line. It isn't, of course. We could actually shade this in. We did that last time. That would be fine. We could shade it in. But what I want you to do is in y equals, I want you to put the answer that you got for the average value, which was 38 over 15. And I'm going to have you graph that, because if you got the right answer, this should look like that the value, the space above that horizontal line and the space below the horizontal line are roughly the same. I mean, it should look convincing to you. So, and I think it is pretty convincing. I'm going to move mine down so I can actually touch my screen. This piece right here and this piece right here, they look like they're the same area. So if you had gotten an answer and it looked more like, let's say, this, and you graphed this, you would know I made an error, right? So this is just one of those really quick check steps that you can make sure that it seems reasonable. Make sense? You have to be careful. You have to make sure that your y and that your window work looks right. Yeah, your window has to go from 4 to 9, because if your window went something different, then you would get a different sort of impression of what the right answer is. Yeah. So you do have to be a little bit careful on your window, but you should get a convincing graph to see that there's a balance in the amount of area above the horizontal line and below it.
Where did you do your window as?
I did my window from 4 to 9. That's the value that has to be correct, because that's what your limits of integration are. And then we just used 0 to 5. Basically just based on the fact that we're taking the square root of 2 and the square root of 9, so the answer should be between 2 and 3. So 0 to 5 is a pretty reasonable number. All right, let's take a look next at 4, 5.